Hey everybody. So in the last couple videos, we talked about how we can describe a line in three-dimensional space. In this video, we're going to talk about planes. Right? So what we mean by a plane is going to be, the easiest analogy is just a piece of paper, but extending infinitely in all directions, right? It's a two-dimensional object, so think of it infinitely flat, just like a line is infinitely thin, right? It's one dimension. So we want to do a very similar thing, actually, that with a line we could describe it with a point and a direction. We're going to do the same thing with planes. We're going to use a point and a direction. So let me sketch the idea we have here, right? So here's a plane, right? I'm just drawing a portion of it. So again, imagine it's extending in all directions. And if you imagine, right, vectors in this plane, right? There's lots of different vectors that live in this plane. So I'm imagining it's almost like maybe I should have just used the piece of paper. This piece of paper is a plane, and each of these vectors is in it, right? So it's very hard to decide which one of these gives the direction of the plane. It's going in all of these directions, okay? So the clever idea that someone figured out a long time ago was what we can do instead is choose a vector like this. This is a vector that is perpendicular to this plane, okay? What I mean by that is if I take any of these vectors I've drawn here and move their terminal point, their initial point to the initial point of this vector, right? All these vectors that live in this plane, right, are perpendicular to that. That's what I mean by perpendicular, right? So, right, if you can tell, this is the pen going straight out of this paper. Any vector in this piece of paper is perpendicular to it, okay? So that's the vector we want to choose, right? And we usually give it the name n. However, I said the vector, and that actually isn't sensible because I could also have this vector except only half as long, or 5 times as long, or facing down. And in fact, that will work as well. It's similar to lines where we had some choices, but the choices all gave us equivalent constructions, right? Things that will still spit out the same points. And so we've reduced our set of possible vectors to all the ones parallel to the first vector I drew, right? So any scalar multiple of that other than the 0 vector would work. So again, it could be a vector pointing down. That will have the same property, that it's perpendicular to all of these vectors that I've drawn in this plane, okay? Now, given that direction, right, you can imagine maybe, right, I'm going to try to draw several planes, right, on kind of floating above each other, and they would all have this same perpendicular vector, right? A vector perpendicular to this one would be perpendicular to this one and perpendicular to this one. And what would we need to do to know which of the infinite number of planes, once we have a direction, is we pick a point. And only one of them is going to go through that point. And then we would know we're talking about that vector. So those are like the 2 pieces of information that we need, right? Similar to lines in the plane, right? If I tell you the slope of a line, there's an infinite number of lines that have that slope, but as soon as I tell you a point, only one of them hits that point. Right? Or vice versa, if I give you a point and tell you I'm thinking of a line through that point, there's an infinite number of lines through that point. But if I tell you the slope of the line, then there's only one that satisfies that, okay? So that's kind of our big idea here, okay? What we're thinking through. We want to describe a plane using a single vector and a single point, okay? So let's work through that construction. So here's the idea. Let's start with, here's our plane. What we want is, given a point and this vector that I talked about a second ago, so let's start with those. Here's a plane. Pretend that we know a point in this plane that I'll call P0, which I'll give coordinates x0, y0, z0. And we have this vector that I was calling n. All right, so I'm going to just draw it like this. This is n. We call this the normal vector. That's the name we give to n. It's the norm, a normal vector to the plane. Sorry, because it's like I said, there's multiple options here, infinite options here. So we call any of them a normal vector to the plane. Right? We want to come up with an equation that describes or that is satisfied only by other points in the plane. So if I pick some arbitrary point in the plane that I'll call P of x, y, z, I want an equation that only points in this plane will satisfy and points out of the plane won't, okay? So here's what we're gonna do. Here's the origin. I'm not gonna draw the axes because it'll make this picture very confusing. So I can draw from the origin to the point P naught, a vector that I'll call R naught, right? And this, of course, would have components in component form would be x naught, y naught, z naught. And then we have a vector from the origin pointing at any arbitrary point, right? So remember, this represents any point in this plane. And so I'll take the point, or I'll call this vector R equal to x, y, z. Okay. And let's give components to n. So I'll use n. I'll call it A, B, C. Okay. Remember, these are given, so these are known things, and then this is some arbitrary point that we want to come up with an equation that only points in the plane would satisfy this. Well, here's what we can do. What we know about this vector n is that it's perpendicular to the plane, meaning, remember, it's perpendicular to any vector that lives in the plane. Well, if I take the vector that goes from this point to any other point in the plane, all right, so this would be the vector r minus r naught, I know that this vector has to be perpendicular to n, right? This has to be, or orthogonal, this has to be a right angle in there, okay? So with that in mind, let's write a few things out. What we can say is that this vector here is orthogonal to n. Well, remember what that means. That means that n dotted with this vector, r minus r naught, has to be 0. Okay? Now, let's convince ourselves, just with our imagination, right, that this only works out for points in the plane, right? So if these angles, if this angle in here is a right angle, so what you should really be imagining right now, for instance, is a piece of paper, right? And if I have, this would be my normal, right, coming out of the paper. This is a vector in the plane, pointing from the point in the plane here to some other point in the plane. They're going to be perpendicular. If I point at a plane, not a point not in the plane, that angle has now changed. It's not orthogonal anymore. On the other hand, if I point at any other point in the plane, I'm just rotating around, right? Maybe I'm shrinking or extending, but it's going to leave that angle the same, okay? So that's the idea, that points not in the plane won't have this right angle. Points that are in the plane will have that right angle, okay? So this is our equation. This is the vector equation of a plane, right? You just need to know n will be known and a point will be known that we use to define this vector r naught, and this represents arbitrary points in the plane. We can write this out a little differently. Let's do just a little bit of work. We've got n is ABC, r minus r naught, so let me just do a little work off to the side here. ABC, that's n, dotted with r minus r naught. Well, r is the vector x, y, z. R naught is x naught, y naught, z naught. So this is x minus x naught, y minus y naught, z minus z naught. So when I dot these two things together, I get A times x minus x naught plus B times y minus y naught plus C times z minus z naught. All right? That's the dot product of n and r minus r naught. Well, what does that mean? That means this equation, A x minus x naught plus B y minus y naught plus C z minus z naught has to be equal to 0. All right, and now you can see if we know what n is, what A, B, and C are, and we know x naught, y naught, z naught, then any point, any triple x, y, and z that satisfies this equation is a point in this plane, right? And with some pretty obvious algebra, you can expand all of these. Remember, you'll get ax and then a times x naught, that's a constant. So if we expand everything and collect our constants, another way to write this equation is ax plus by plus cz plus d equals 0, right? So either of these are known to be equations of the plane, right? Notice these are linear in x, y, and z, right? And a line in 2 dimensions is linear in x and y. Neither one of them is squared or a root power or something like that. They're just simply to x to the first power, y to the first power, right? They're linear functions of x, y, and z added together. That's what we mean by linear in x, y, and z. So that's our equation of a plane. So let's do a little exercise of finding the equation of a plane given a scenario, okay? So we have, let's say I want to find the equation of the plane that contains these 3 points, 1, 1, 0, 1, -2, 2, and 0, 0, 2, okay? So this is another geometric idea. Any 3 points, as long as they don't all lie on one line, define a plane, right? And I always think about this as, right, if I have 2 points, it defines a line, right? So now imagine, draw this really quick. I've got, oh, I guess it doesn't want to show that. All right, I've got a line, right? Well, I can, and this plane contains it. If I rotate around, there's an infinite number of planes that contain that line. But if I pick a third point, so I have 2 points on this line, if I pick a third point, right, that's the only plane that contains them, right? If I could rotate this paper and leave that point behind, it wouldn't contain it anymore, right? Obviously, it moves with the paper, but if it was just a point floating in space, our plane would not contain it anymore. So I've got 3 points sitting in space. Let's write these out. Let me remember how let's see. Okay, let's call this one A is going to be 1, -2, 2. We'll call this one B, 1, 1, 0, and then this one 0, 0, 2. So those all live in some plane, A, B, and C, okay? Maybe I'll draw that in. I'm not trying to be accurate about where they are in space. I just want to give myself a little representation. So remember what I need for my plane equation. I need a point, so I can define a vector to that point. That's easy enough, right? I can pick any of these points to be R naught. The other thing I need is the normal vector. And here's the idea that we can do. I've got these 3 points. I can think about a vector here and a vector here. I can choose any combination of vectors I can make from these. I just happen to choose these, right? And I'll call these U and V. If I take the cross product, U cross V, I'm going to get a vector perpendicular to both of them. And it turns out that's going to be perpendicular to all of them, right? Again, the easiest way to see this is just to imagine any flat surface like a piece of paper, right? If I have a piece of paper and I've got two vectors in that paper and I take their cross product, I'm going to get a vector pointing out of the paper. And any other vector in the paper is going to be perpendicular to it, okay? So I'm not exactly proving that, but we're gonna take that as true. So I can compute this vector fairly easily, right? Remember, there are many options for n, so depending on which you chose to connect as your vectors, you get different responses. I chose what I chose. So what I've done is I've got, let's see, I've got u is equal to, I took the vector going from A to B, so that looks like 0, 3, -2. V is going to be the vector from A to C. So that looks like -1, 2, 0, right? Those two vectors. And so if I take U cross V, now I'm noticing I actually drew this incorrectly. U cross V, because of the right-hand rule, should be pointing into the paper. I just sort of drew it as I drew it, but it would actually be pointing down into the paper. But let's just compute the values here. U cross V. So let's see, I take 0, 3 times 0 minus -2 times 2 gives me a +4. I'll take -2 times -1 is +2 minus 0 times 0. That gives me 2. And then I can take 0 minus 3 times -1 gives me +3. So there's the cross product of those two vectors, gives me my normal vector n. Okay, so let's come up to our equation now. I've got n is equal to 4, 2, 3. I'm going to choose R0 to be equal to 1, 1, 0. So I just picked that point arbitrarily. And so now writing this equation looks like 4, 2, 3 dotted with x minus 1, y minus 1, z minus 0 equals 0, which if we write out looks like 4 times x minus 1 plus 2 times y minus 1 plus 3 times z equals 0. You can also expand this and end up with 4x plus 2y plus 3z. You'll get a -4 and a -2, -6 equals 0. And that was that alternate expression for the plane, right? ax, by, cz plus d gives us 0. Okay, let's double check. Let's check that the points I have here satisfy this equation. For instance, 0, 0, 2 gives me a 0 here, a 0 here, a 6 here, -6 is 0. Or 1 minus 2, 2. I get 4 minus 4 is 0, plus 6 is 6 minus 6 is 0. Let's do the last one, 1, 1, 0. I get 4 plus 2 is 6, plus 0 is 6, minus 6 is 0. And so all 3 points satisfy this equation, right? Doesn't prove the whole plane does, but it makes me confident about the work that we've done, okay? And that's it. This is the equation of a plane, and this is the basic idea, right? There's, usually our job is, if we're not given the normal vector and a point, we might have some other conditions and we have to figure out, like in this case, given 3 points, we found the normal vector with a cross product. There are some other scenarios we can imagine that we can do in other videos. Let's take one look at this in a graphing program, so the picture might be a bit better. So let's take a quick look. So here I have, again, using GeoGebra. Here are the points A, B, and C. I'm not 100% sure I named them as I named them before. I believe I did. But in any event, there are 3 points, right? And what we did was we created vectors between them. right? So now I have vectors. I picked one point and created vectors between the two of them. I know those are the same two vectors I chose, right? So I'm just kind of scrolling around to see different angles. Then we computed their cross product to get the normal vector. Right, so there's my normal vector. Notice that it's perpendicular to both of those. I think we can kind of see that, right? When we look at this angle, we see that right angle sitting there. And let's now put in the equation of the plane we came up with, right? So if you can see, those two vectors are living in that plane. The normal vector is, oh, something's off. I must have an error. Oh, I moved one of my vectors when I touched it for you guys. Let's see if I can get it back to where it was. Sorry, I see these values over here are now all way off because I moved things around. Give me 1 second. Let me just re-enter those values when I see what U and V are. So, oh, I got to change it up here. I moved the point around. Okay, I only moved 1 point. Sorry about that. So this has got to be the point 1, -2, 2. Okay, sorry for that. All right, now we can see that those vectors live in that plane, right? They're sitting flat in it, right? As we look around, we can see that the normal vector appears to be sticking right out of it as we anticipated. And I think we can imagine if we drew other vectors in that plane from that normal vector, they would all come out and be perpendicular, right? So that's the idea. I hope this graphic helps a little bit. I know it can be a bit confusing to try to organize these things. So this, I think, is our correct orientation, where the red axis is the x-axis, the green one is the y-axis, and the blue one is the z-axis. We see the normal vector coming out at us here, and we're kind of facing this plane more or less head on. Okay, that's it. Thanks, everybody. I will see you next time.